All right, well, good morning, everyone. Again, it's great to be here. Today, I'm going to provide you a real quick overview on multiple ways to look at drought using soil moisture data. So basically, two different contexts. Before we get into that, there we go. Just click the screen. Before we get into that, I want to get a little bit into why. So if you haven't seen this map, you're probably going to see it some more. This is courtesy of drought.gov and some of the great folks, Rocky, Stephen, sorry I saw in the room. This is a new map showing you where in the United States we are currently monitoring soil moisture, or at least those who are willing to share it with us. So it gives you a really good indication of, yeah, we got a lot of data. Really glad to see CISESS kind of take it on. So hopefully you guys can expand this out and capture all this information. But the challenge with utilizing that data for drought monitoring is that you need some sort of context to give drought meaning. So when I say it's dry, well, dry compared to what? Most folks who are climatologists, we put on the climatology hat and we're like, well, let's compare this to, the last 5 Mays over the past 30 years or something. And so you need a historical context to ground information today that you're seeing in order to understand, am I dry? So once you have your 30-year baseline, which is kind of your typical approach, you're looking how far you are below that. That gives you the anomaly. And then you convert that to a percentile, and that gives you the rarity of an observation. If you look at this graph here, I stole it from this manuscript. You kind of see at the bottom. It doesn't show the state mesonettes, but you can see if you required 30 years of data, the number of stations that you could produce a 30-year climatology with is maybe a handful, tens of stations. If you relax that to 20 years, you're kind of talking about hundreds. But on that map I showed earlier, there's thousands of stations. And so we're really not capturing the full potential of this network using a historical approach. And so my question is there another way? So I had the opportunity to work on a data value study with the Upper Missouri River Basin. I got to lead the mapping project. And one of our goals was to develop a suite of soil moisture products we could put online that folks can interpret, that can provide information to drought monitoring in other communities with very short records. So less than a year, some of these stations. And we played around with various different products, but the one I'm going to talk about is fractional available water. Thank you, Vinit, for talking about that and setting that up. But basically what you're doing is you're looking at the soil type, you're sticking the sensors in, you're extracting wilting point and fill capacity. So fill capacity is kind of the upper limit. If you exceed that, plants are going to be able to access that water because it's going to drain through the system before the roots can have access. There's a lower limit wilting point. So as soil moisture approaches that, plants are going to struggle pulling water out. Some plants have a different wilting point. We're kind of just doing a broad estimate for agriculture using this approach. But basically, you have those two ranges and you're kind of figuring out where does my observation fit between those two. If you're at wilting point, you're 0. If you're at 1, that's fill capacity wet, that's good. If you want to prevent drought. So the idea is, we have these two different approaches. One requires no period of record at all, the soil context. One requires a significant period of record. So we wanted to kind of stack these two up and use data from the U.S. Climate Reference Network. It was mentioned in a couple of the talks. This is the map showing you where those stations are located. We have about 114 in the CONUS, and we have data since 2010. So this allows us to do some statistical processing to kind of guess what the 30-year normal might look like, and we can compute anomalies at all these stations. And then we can also use the same process we applied to the Upper Missouri River Basin, compute fractional available water at all these sites, and compare and contrast these two contexts for soil moisture and how they respond to drought. So this first graph I'm showing here on the top left is soil moisture anomalies, and on the just a little bit over is fractional available water. And we're doing it by U.S. Drought Monitor. I'm showing you kind of the range of the anomalies and the fractional available water by USDM category. Probably not my favorite way to look at these, but it's kind of a sanity check. But basically, if you look at the anomalies, there's a dry down from none, which is no drought. You're kind of above normal, maybe even. D0 is kind of abnormally dry if you're familiar with the drought monitor. Drought doesn't really begin until you hit D1. D4 is kind of the worst category. And you see it steps down from none to D0, and then it kind of levels off for soil moisture anomalies. You don't really see further declines, at least in the interquartile range, which is what I'm looking at. For fractional available water, we actually see a stair step as you move down through worsening drought conditions based on the drought monitor category. So it's just an interesting feature to kind of point out. The next thing we did was we took all of these stations from 2010 to 2024, and we identified all the times we had drought. So drought begins the first week you're at D1, And so for this first graph here, I'm showing you weeks since onset. So that's the top graphs. And on the left, I'm showing soil moisture anomaly in orange, fractional available water in green on the right. And negative values on that x-axis means drought hasn't started. So those are weeks before drought. Zero is when drought begins. Positive values, drought has started. And if you look at both of these products, they're showing declines in soil moisture conditions prior to onset. And you really see it beginning to pick up about 6 weeks out for both metrics. Fractional available water, 0.8, is pretty wet. I have a hard time justifying 0.3 standardized anomalies as wet, but it is above normal. It's above the zero for the anomalies. We did the same thing coming out of drought on the bottoms. So this is weeks since termination. Negative values, you're still in drought. Positive values, drought has ended. And you see both of them showing an increasing trend in soil moisture conditions as you're coming out of drought, with a spike the week right after drought. So I guess there's an impulse of rain coming through that's kind of wetting the system up, and then you kind of relax. The final thing we looked at was how are these values varying through the evolution of drought. I didn't have a lot of time to kind of set this up, but basically what I'm looking at is the distribution of standardized soil moisture anomalies on the left again, fractional available water on the right. The pre-drought period is 6 weeks before onset. So before that first week, you start drought. You can see they're kind of hovering around normal. Fractional available water's got values all the way up from 1, which is super wet, all the way down to wilting point. It's a very broad range. But as you step into drought, so that's the orange phase, this is drought onset. So drought's begun, and you're continuously intensifying during this period till you hit your maximum drought category. So whatever that is, it could be D3, D4, it's different per event. So that's the onset phase. So that's where you see some of the driest conditions for both measures. And then when we get to the main phase, so that's when you're at D3 and you stay at it for a while, or it's the last week you're at D3. So this is your main phase. You're at your kind of your, I guess, mature state of the drought. And then the green is showing the distribution as drought's ameliorating. So you've come off your peak, your drought's not over yet, you haven't hit D1, but you can see both metrics show a pop in the soil moisture values. So we have really wet conditions in drought, which is a little confusing. That first graph I showed where you could have a broad range. We're capturing amelioration phase and onset phases there. And then for the post-drought, this is the 6 weeks after, you see there's kind of a relax in the two measures. So one of the main takeaways, both measures actually did a really similar job. None of them I saw outperform the other, at least at a national scale. We're digging into some of the regional results right now. I didn't have time to put them into this, but I think one of the key takeaways is that if we use fractional available water, we're getting just as much information about drought as we are using a historical baseline approach. And so you can start thinking about using all of the soil moisture stations on that first map I showed. Fractional available water, as long as you have a good handle on what wilting point and fill capacity are, you can use this data for stations with less than a year to 30 or more. And this allows us to broaden the pool of soil moisture observations that can go into our monitoring products. And I kind of did some real quick statistics. I built water retention curves for all the stations on that map and estimated how much water sits beneath the stations. So that comes out to about 1.5 million liters of water just at the lat long for that site. I know Vinette said you don't do this, but I've gave a representative area as well. So I did a 50-kilometer circle, 50 square mile circle around each station. And that amount of water comes to 143.5 million hectacre feet. That's enough water for every home in America for 40 years. It's a pretty significant chunk to be ignoring or not utilizing in some way to improve our monitoring processes. So with that, I yield back and look forward to the questions at the end. Thank you.